Hey, hello everyone. Welcome to the second lecture for the GATE question papers 2019. The first test I did question number 9 to question number 13, and you can find that link in the description section of this video. And today I will be doing question number 14, 15, 16 and 24. So as you know, I am doing only the organic questions of the GATE questions, and I am doing in a series 5 questions in a series, but in this question number 2019 GATE there were lesser organic questions, so that's why I am doing 4 questions hereafter. Okay. So let's start with the question number 14. It asks, among the following compounds, the number of compounds that do not exhibit optical rotation at room temperature. So they are given lot of molecules, you can see here, and they are asking which one do not. So this was like even if one mistake you do and you lose your marks. So we have to be very careful with such questions, and if you are not very sure, it is better to leave, because negative mark is never good thing, right? What is very important is, if molecule has to show optical activity, it has to be asymmetric. See, stereoisomers, sometimes diastomers are there, but they might be optically inactive if it is meso compound. But if it is asymmetric, it has to be optically active. What do we mean by optical activity? You should understand first. Optical activity is when the molecule is exactly same, they have all the physical and chemical properties same. Only thing is directionality changes, like one substituent on the same carbon you have replaced with other substituent. Now nothing else can make out the difference. The only difference which it shows is it rotates the optical light in different way. So what I am trying to say is that small difference is needed, and therefore if that small difference is there, then only that optical difference will be seen. That means they should have pair of enantiomers. If pair of enantiomer is not there, that means optical activity is not there for that molecule. Pair of enantiomer is one molecule is rotating towards right, one molecule is rotating towards left, because that's the only way to differentiate between them. Okay. So somehow we think that no, first we have to draw mirror image, then we have to see mirror image is just that it happens to be mirror image. Basically two of the substituents, they exchange their position, that's all is enantiomer. Okay. Let's look at the molecule one by one. So basically if a molecule is symmetric, then what happens? Symmetric means a plane of symmetry. Plane is like a paper, two-dimensional paper. If it crosses through it and you see that it is exactly dividing molecule into two identical half, then what happens? Even if you draw the mirror image, you will see that it will superimpose on the initial molecule if you rotate it properly. So that means they both are one and the same. If they are one and the same, there is no difference. What kind of activity it will show? It cannot rotate, one cannot rotate in one left and one in right, because they are same, and therefore they are optically inactive. Okay. Now let's look at the molecules. Now this molecule is definitely asymmetric. Why? This start carbon is chiral carbon. All the substituent here are different. One is CH3, one is phenyl ring, one OCH3, one H. Try however you want. Okay. You draw like something like, imagine this board itself, this screen itself as a plane. So you are able to divide this CH3 into two identical halves, this pH into two identical halves, but outside the screen is OCH3, inside the screen is H. As much as you try, you will see that you cannot find a symmetrical plane, and therefore it is optically active and it will have pair of enantiomers. How to make? Just exchange any two groups. You can exchange H with CH3 and CH3 with H, or H with OCH3 and OCH3 with H. So whenever you are exchanging the substituent, you will see that what you are getting is a mirror image, but it will not be superimposable. So if it is not superimposable, that means it is different, and therefore they are different, and they are optically one of them rotates in left, one of them will rotate the plane polarized in light, and therefore they are optical isomers. So here what I have done is I have exchanged, I have put H in place of OCH3 and OCH3 in place of H. So now I am having A and B as two different molecules. Now I am trying to show you that how A and B are mirror images to each other, because once you have exchanged, they are not very clear that they are mirror images, but in a short span of time I will be able to explain that these two are actually mirror images. So I am taking this B, where am I? Here, yeah, and I am rotating in 180 degrees like that. Okay, so when I rotate 180 degrees like that, so pH has gone back, H has gone back, OCH3 has come front. Now you put it in front of A. Now this was the A which I had initially we had drawn, and this is the B. Now you see that they are mirror images to each other, and try as much as you want, you know, if you rotate and put it on this. So something like this. Okay, this CH3 you put on this, so you will see that this CH3 superimposes on this. That time this pH also superimposes on this, but this H is not superimposing on CH3. Similarly, this OCH3 is not superimposing on H. So they are not superimposable on each other, but they are mirror images. So they are enantiomers, and therefore they are optical isomers to each other, right? Moving on to the next question, next choice. This is the system which they gave. So this was not even allene. Allene has two double bond next to each other. Now it had three double bonds. So we have to find out how are these two substituents. Are they perpendicular to each other or they are in the same plane? Okay. So first we have to understand the pi bond, right? So let's start with this. So I am starting with this system. So there is a pi bond between just one sec. Yeah. So there is a pi bond between these two carbon. Pi bond means what? There is an unhybridized p orbital which is parallel to each other and they are overlapping. So imagine this p orbital is parallel, this and this p orbital, they are overlapping, right? Now this carbon is forming pi bond even with this. So this p orbital is already involved, so another p orbital has to be perpendicular to it. Perpendicular means this is coming outside the board and this is coming inside the board. So now even this one is coming outside the board, so this perpendicular, this p orbital is coming outside the board and inside the board. Sorry, I have drawn it other way, but yeah, that's what I mean. So what happens if this p orbital is perpendicular, then this plane of molecule has to be perpendicular to that p orbital. So these two COOCH3 and this hydrogen is on the screen. Now moving on to this bond, so same way you can see here, I must have drawn down, so let me go down and show you. So we already saw that this p orbital is involved in pi bond with this. So if it has to form pi bond with this p orbital has to be perpendicular. So this orbital is coming outside the screen, this is inside the screen. Similarly, this one is outside the screen, this one is inside the screen. So if this is inside the screen, this outside, you understand, this is perpendicular. So that means this H and this COCH3 is in the plane. So now basically you are having something like this. Now COOCH3 have made a bigger sphere, hydrogen have made a smaller sphere. This is again a smaller sphere and a bigger sphere. So imagine this board itself, as a plane, the screen as a plane. So what it is doing? It is dividing the molecule into exactly two halves. So this big sphere is cut into two. So identical half is front of the screen, identical half is behind the screen. Similarly, this half, this smaller ball also, identical half is front and identical half is behind. Same way this, same way this. So these two, this is basically symmetrical. So you can even draw the mirror image and see that they will be superimposable on each other. So this is what is the mirror image, what will look like, what it will look like. So when you look at the mirror, you always see your nose front, right? So because that is what is front. So from here when you see, because this side is H, so it is H here, COCH3 is front, COCH3 is front, rest all is same, and then H is down behind, H is down behind, and this is there. Now these two look like mirror images, but actually they are superimposable. So if you rotate it 90 degree, 180 degrees like that, okay, I am catching this COH3 CH3 and pushing like that. So this COCH3 comes here, this H comes here, and this one has moved here and here. So, you can see that these two are superimposable on each other. So, they were identical. So, it is definitely not optical isomers, right. Moving on to the next molecule. Now, this molecule has a chiral center here very clearly, okay, because this carbon has 4 different substituents: hydrogen, CH3, this side's carbon is different, this side carbon is different, and therefore, if you draw the mirror image, you will get this, and try as much as you want. You just rotate it round, you will see that this whole part will sit. But what happens, because you are rotating 180 degrees, CH3 goes behind, H comes front. So, CH3 and H will not superimpose, this H and CH3 is not superimposing. So, therefore, it is optically active, okay, they are enantiomers. Now, next molecule, okay. Now, you can do with this also Sawhorse projection formula, but it is better to convert them into Fischer projection formula. So, in Fischer projection formula, you can very easily make out a molecule is meso or not. That means, does a plane of symmetry run through it or not. So, how to convert this Sawhorse into Fischer? You first make it into eclipse conformation. So, this COH is bulky, this COH is bulky. We will try to put them both next to each other. So, what you can do is just rotate it 180 degrees down. So, what happens? This COH goes down, this also rotates 180 degrees. So, this OH goes above, it was below the plane, now it goes above the plane, but it goes away from the viewer. Similarly, this H comes above and it was away from the viewer, but it becomes towards the viewer. So, that is what I have done, and we get this, and then I had little bit I have rotated down like that. So, that these two COH comes here. Now, in Fischer projection formula, what happens is, it basically has 3 bonds on each carbon, okay. 4th is also there, of course, but yeah. So, what is on vertical line is away from the viewer, and what is in the horizontal line is towards the viewer. So, we have to rotate it like that. So, I am going to rotate it 90 degrees. So, that COH goes away from the viewer, and now both of them have come front, but H goes on the right side, OH goes on the left side, both of them are front. So, now I can draw in the Fischer projection formula. Now, because COH is away from the viewer, it will go in the vertical line COH, and these two are towards the viewer. So, they will be in the horizontal line. You can see H is on the left side, so write H on the left side, and you can see OH is on the right side, so write OH on the right side. Same thing has happened here also. So, COH has gone behind, this H is here and OH is here. So, basically you are getting like this, right. Now, you see very clearly plane of symmetry runs between it. You imagine a paper cutting into half. So, from here you go little bit front, you are seeing H. If you go same way this much, you are getting H. If you go this much distance, you are getting COH. You are going this much distance, you are getting COH. So, these are exactly 2 identical halves. So, it is one of the stereoisomers, but by itself this is optically inactive, because this is meso compound, a plane of symmetry runs. Even if you draw a mirror image, you will see that it is not a mirror image, but it is same thing. It will be identical, it will be superimposable on each other, right. So, I drew the mirror image, and then what you see, I get COH, OH is front this side. So, this OH has to be here, same your nose you see first, and H is behind. So, H is behind, and similarly this H is behind. So, this H is behind, OH is front. So, OH is front. Now, what you do, you rotate this B 180 degrees. Now, one thing is very important, please remember this, you cannot rotate Fischer projection formula like that you rotate it, just lift the whole molecule and rotate it like this behind the screen. Why? Because you understand, you have made 3 dimension into 2 dimension. So, this hydrogen and this OH are actually coming outside the screen. This H and this OH both are coming outside the screen. So, if you rotate 180 degrees, H goes behind, OH goes behind. So, it does not no longer remains the same. So, you cannot simply rotate like that. What you can rather do is you can rotate it in the plane. So, in the plane of the paper you can rotate 180 degrees. So, I am putting this UH down, this UH down, so that what was outside the screen still remains outside the screen, just I have rotated 180 degrees. And so, what we get, we rotate like that and we get here. Now, what you do, now you will see that A and B were superimposable on each other. So, this is B and that was A. So, in B what happens, both the OH are on right side, on A also if you see both the OH on the right side. So, they are superimposable and therefore, it is optically inactive. This molecule, okay, this molecule was very confusing. Initially I thought they are optically active, but later I realized that these two substituents are very small. Unless you have something like PPH3, no, rotation is stopped. So, what happens is when rotation is stopped, then this molecule is locked in one conformation. So, these two will be perpendicular to each other. So, this F will be towards the viewer, this COCH3 also will be towards the viewer, whereas this COH3 will be towards the viewer and this F will be away from the viewer, whereas this F and this H will be in the plane. In that case, it would have been definitely optical active, and it would have been a concept called as atropisomerism. Atropisomerism means rotation is hindered due to steric hindrance of the substituents and then optical activity is seen. But here such things is not there, so therefore, it is optically inactive. Let us for time being, I want you to explain, see, as I told previously many times, my idea is not just to solve the problems for you, my idea is to teach organic chemistry. Imagine if this were bulky, then how it would have been optically active, I want you to understand. So, what happens if these two were bulky, then this will be locked in conformation and free rotation will not be allowed. Okay. So, what happens, imagine this fluorine has gone away from the viewer. So, this ring is there, it's perpendicular. Okay. So, this part of the ring is outside the screen and this part of the ring is inside the screen. So, what happens, this COH3 is coming outside the screen, this fluorine is going inside the screen. Okay. Whereas, this fluorine and this H are in the plane. So, now if you draw the mirror image, what happens, you are getting same thing, this what is outside the screen remains outside the screen, but this one is this side, right side. So, here it will be on the left side and you get this. Now, whatever you do, you will see that you will not be able to superimpose this on this. Okay. You can try as much as you want, halt it, stop it and think about it. You can think, no, you just rotate it 180 degrees, rotate it 180 degrees. So, this comes and sits on this fluorine comes and sits on this, but once you do that, this H will come outside the screen and this OCH3 will go inside the screen. So, these two are not superimposable. So, they should have been optical active, but at room temperature, because F and OCH3 are small, they will happily rotate around. So, no such restriction is there and therefore, it is optically inactive. Okay, optically inactive. Now, when they rotate, you can see that they will be identical. Now, if it is like that, you can rotate it around. So, this fluorine goes that side and H comes this side and then these two will happily superimpose on each other, right, and therefore, this is not optically active. Now, this molecule clearly has planar symmetry. What is the planar symmetry? Imagine this board itself to be planar symmetry. So, what it does? It divides this whole carbon into two identical halves, all these carbons into two identical halves. This CH3, imagine this as a ball. So, two identical halves. Similarly, bromine is a ball. So, these are this is definitely optically active. Sorry, this is definitely a symmetric molecule. It has a planar symmetry and therefore, it is optically inactive. So, the number of compounds that do not exhibit optical activity at room temperature is 4. Okay. Moving on to next molecule, the number of following molecule or the following dienes that undergo Diels-Alder reaction with methyl acrylate. So, methyl acrylate is not important. What is important here is Diels-Alder reaction. So, what is Diels-Alder reaction? Diels-Alder is nothing but 4 plus 2 pericyclic reaction under thermal condition. So, you have a 4 system, 4 is diene because 2 alkenes are there, and you have dienophile. Dienophile is basically alkene, phile means loving because it is reacting with diene, therefore, it is dienophile. So, this goes and interacts, this comes here and this comes here. For this to happen, very important, your diene should be cis. Okay, it cannot be trans. Otherwise this pericyclic reaction is concerted. In one step, this reaction cannot happen. So, look at this molecule. Happily, this will undergo because in the cyclic form, you are tying it up. They are bound to be in the cis, so they are in the one form. So, this will react, this will also react. Here what happens, you have tied it up. If it is open, imagine somebody gives you something like this, then there is no issue because this single bond will allow rotation. So, this will rotate and this will rotate and then will give you like this. Even for small fraction of time, that is good enough for the Diels-Alder reaction to happen. But when you have when you have cyclic form, this becomes problem because it is locked. So, this is coming out and this is coming in, and then it cannot react. Remember this S form, this is called as S form. Okay, S form cannot react. This will definitely react because it is cis. This again cannot react, this can react and this can react. Okay. So, the number of which will undergo. So, how many are there? 1, 2, 3 and 4 and 5. So, total 5 will undergo Diels-Alder reaction. So, answer will be 5. Just if you do not know methyl acrylate, this is what is methyl acrylate. Methyl is because of in the ester this substituent that comes first, that is methyl. Acrylate is this acryl group, and 8 is because it is ester. Okay. Moving on, the number of proton NMR signals observed in the following compound is. So, basically they have given this molecule and they are asking how many proton signals will be there. So, in proton NMR, no, whichever proton is chemically different, it is in chemically different environment, they will show different peaks. So, I have drawn it in a detailed way. Now, you see the COCH3 is coming out. So, this CH3, these 3 protons are definitely different from all other, but all 3 hydrogens are identical, right, because it is CH3, all 3 hydrogens are identical. If I move from one hydrogen, I am coming to carbon, go down, I am coming to oxygen, same way another hydrogen also. So, these 3 will show one signal. So, I have put them as 1. Now, coming here on this carbon, there is no hydrogen. When I come here, there is no hydrogen because valency of carbon is 4. When I come here again, this CH3, now 3 hydrogens will come as 1, correct. Interesting thing is, see here, it is identical substituent and here also it is identical substituent. So, this CH3 and this CH3 are in the identical environment. If I move one bond, I am getting carbon. If I move one bond, I am getting carbon. If I am moving up, I am reaching same. Moving up, I am reaching same. Go down, go more down, they are same. So, basically these two CH3s are in chemical identical environment. So, they will show one peak, and of course, these 3 hydrogens and these 3 hydrogens are identical. So, it will show a big peak which will have intensity of 6 protons. Moving on to here, so again these 2 hydrogens are identical, you can look at very clearly, because if I move here I am seeing this, if I move here I am seeing this, if I am moving here I am seeing this, if I am moving here I am seeing this. So, this will give another signal, and now this CH3 is very different, but all 3 hydrogens are identical. So, it will show the 4th signal, and when I come here, this acetal protection, all these 4 hydrogens are exactly identical, because I move here I get oxygen, I move here I get oxygen, keep moving you keep getting same thing. So, therefore, you will get totally 5 signals. Last question, this was bit tough question. So, the major product formed in the following reaction. So, remember whenever you have N-butyl tributyl tin hydride, remember this tin hydride will always go reaction in the radical mechanism, and you should also know this AIBN, that is isobutyryl nitrile, butyronitriol. This is used always in catalytic amount just to start the reaction, okay, to start the first radical formation. After that propagation will happen, reaction will keep continuing. So, you need very little just to start, okay, AIBN, and it is giving you lot of choices. You have to know which is the right product. So, AIBN, what happens, it is bound by 2 nitrogen double bond. Now, you know nitrogen is a wonderful leaving group. Why? Because nitrogen is very stable, triple bond, okay, that is why it is used as inert gas. Many times we do organic reactions, we need inert atmosphere. So, we put under nitrogen atmosphere because nitrogen is very stable, triple bond. So, lot of energy has been released, very stable. So, this breaks up and you get this. This is the initiation, not initiation, this is the first formation. Initiation is when tributyl tin hydride gets its first radical. So, this proton is taken, this becomes very stable. Now, this will not react at all, this is normal alkane, but this itself is good enough, it will continue the propagation. Now, tin will always react with halogen group. Why? Remember, carbon halogen bond is weak, especially if it is iodine, it is very weak, because iodine is very large in size, and because iodine is very large in size, so this bond is very weak, they break easily. Little bit also light, this breaks up, this comes here, this iodine is taken by this butyl, and you are getting this. Now, this is what is formed. Now, what we have to see is where the next radical will form, because this cannot stay, radicals are very unstable, and especially this is primary radical, very stable. You should know radicals are electron deficient in nature. So, they behave like carbocation. So, carbocation, you know, tertiary carbocation is more stable, then secondary, then primary. Similarly, tertiary radical is more stable, then secondary, then primary, as you can see here, because it is electron deficient. So, if it is tertiary, this will pump electron, this will pump electron, this will pump electron, and they give lot of electrons here, and therefore, it is stable. Then comes secondary, then primary. So, that is already formed. Now, another thing is there, on the carbonyl carbon, if you get an electron, then this is stabilized by the electron on the oxygen. Oxygen has lone pair. Now, this is more stable even compared to tertiary, and therefore, this is very nice bond to break, because you got a radical here which will be stabilized by the electron on oxygen, and therefore, you have to understand this is the bond which will break. So, alpha to carbonyl is always labile for radical reaction. Please remember this, you cannot forget this hereafter, okay. So, alpha sigma bond to the C double bond O is always labile for radical reaction, because a carbon on the carbonyl carbon, the carbon of the carbonyl carbon, if it has electron, it gets stabilized by resonance through oxygen's lone pair of electron, fine. So, let us break that and see what happens. So, you are getting one electron here, and these two will and why it is fine, because this will come here and this will come here, right. So, next what happens is this immediately forms bind with pi bond. Why? Because pi bond are very labile, you know, sigma bond is always stable, pi bond just next to it. So, immediately it breaks and it forms a double bond here, and you are having oxygen with electron. Now, what happens? Sorry. All I am saying is why this broke. Another reason why it broke is this electron which is coming here is also stabilized by resonance from this carbonyl carbon, because this breaks away. this we anyway told why it is stable. This also is stable because of the resonance. And now this electron, because this bond was labile, we already told bond alpha to C double bond O is labile. So, this is what has broken, and so now this forms bond with this, and you are getting one electron here. Now, this will propagate easily. How? Now, tin butyl tributyl tin hydride, it does not need AIBN because already a radical is there. This radical picks up proton and it breaks away, and you are getting this one. So, your answer is A. Okay. So, what we understood in this question is, first is wherever halogen is there, let us look at it again. So, let me just erase them. Yeah. So, few points to remember is tributyl, this will give electron. So, sometimes even without AIBN, if you heat it little bit, you get this radical. Then this will cleave first this one. So, it will always cleave the most labile bond. The most labile bond is always carbon halogen bond. That should be very clear, and the halogen goes to tin and you get here. Then you have to look at the second labile bond. The second labile bond is towards this carbonyl alpha bond. Why? Because if you get an electron, this gets stabilized by this electron like that, and also this electron is getting stabilized through this resonance. So, this is what happens, and therefore, this breaks up and this forms ring, and this takes away another hydrogen from the next tin butyl hydride, and that is how you get your product. Okay. That is it for today. Thank you very much.